All right. Welcome back, everybody. Math 131, Lecture 15. Today we're going to look at a couple applications of the natural exponential function. And the joyful part for you is you've done that in pre-calculus already. However, there's one new little part, and that's called a differential equation. We're going to look at a very, very simple differential equation. We're going to memorize the solution, and the solution will send you to what you learned in pre-calculus. So it's a new little topic differential equation, and then you'll just solve it, and then you're back to your pre-calculus. Then we're going to start, very important topic, anti-differentiation, which is integration. We're reversing the process of the derivative, finding the derivative. Now we're given the derivative. Tell me what the function is. So we're going anti-differentiation. We've been doing differentiation, finding the derivative. Now you're given the derivative, find the function. I like to do Chapter 6.1 and Chapter 9.1 together because it's very, very essential that you're good at this. And I like to hit 9.1 early so that you keep working at it. It's integration by substitution. It's a must for being successful in the next class. Got to be good at integration. All right, so we're about ready to start, except that I had a question right before we started, and it had to do with how do you input this in WebAssign. When you have natural log of x as your answer, looking at it like this is perfectly great. If you had natural log of x plus 4, if you mean that x plus 4 goes with the log, you definitely have to use parentheses. Well, for WebAssign or mathematical software, they're looking at natural log as a particular function, and you have to put in parentheses the argument. So when you're doing WebAssign, you just can't type ln(x). You have to type in natural log parentheses and tell it what the argument is. So on your homework, if you were typing in natural log x, which is a perfectly okay way to look at this, but if you type in ln(x), the software thinks you're just putting in some letters. Okay, but that tells it's the function, and there's the argument. Just like when you did e to the x, you had to type in exp parentheses x to tell it what it was. Okay? All righty. Let's begin Chapter 5, Section 1. We're going to do 1 and 2 really together. The new concept, of course, is the differential equation. I'm going to remind you of what you already know, and then we're going to build on that. If you'll have your book open to page 284, Chapter 5, Sections 1 and 2. And we're looking at the applications of y equals a e to the bx. Your natural exponential function, a being a constant not equal to 0, b being a constant. All right, so what you recall is that whenever the b is greater than 0, b greater than 0, like y equals e to the 3x, y equals e to the x, you would have your exponential growth function. We call that growth. And when your b is negative, whenever your exponent e to the minus x, e to the minus 2x, when b is negative, what does your graph look like? Yeah, it's your decay. We call this decay. Decay. All right, so when we have applications, along this axis you usually have time. When we're looking at an application, along the x-axis we usually have time, and along the y-axis we usually call it some kind of population, maybe P for a population, or A, an amount of money, and we don't usually go negative, so we don't usually have that part. And so the formula for this curve, who remembers? P of t equals, I always tell my class, think shampoo. Pert, P sub 0, e to the RT, like pert shampoo. All right, this was the form that you probably memorized in pre-calculus for a population growth. That population might be people. It might be bacteria. Or it could actually be money that you have in an account that is growing compounded continuously. Money when it's compounded continuously, which is very close to compounded daily interest, and it just gives you a quick and easy way to make some wise decisions. All right, so P of t equals P sub 0 e to the RT. The little P sub 0 represents what? The initial amount. That means when time is equal to 0, so your P sub 0 is right here, and it would be growing. So when R is greater than 0, you have growth. All right, and the best I remember in the pre-calculus class, when it was money, it was still the same formula, but they used something like a at t. A, like for a future amount, equals A sub 0 e to the RT. It's just letters. So most of the time I just stick with the same letters. P of t equals P sub 0 e to the RT. All right, if you have radioactive substance that has half-lives, along this axis you usually have time. And along this axis, it could still be considered P, like a population. I think a lot of times a book will use a A. And what they do, instead of using a B, they usually use a lambda. Do you remember seeing a lambda somewhere? So you had things like A of t equals A sub 0 e to the lambda t. And it looked like it had a lot of different formulas, but it's all the very same formula. If R is greater than 0, R greater than 0, you got growth. If you make your R less than 0, you got decay. So I wouldn't get hung up on all the different formulas. All right? So it's still the initial amount. Here's your A sub 0, and it's decaying like a radioactive substance. All right? Now, so what is new for Math 131? Everybody okay with this? It's bringing back some happy memories. So what's new for Math 131? All right. So far, we've looked at derivatives. And here's a couple examples. And I'm going to lead you, what I'm doing is leading you to what's called a differential equation. A simple, one of the simplest types of differential equations. So differential, D-I-F-F-E-R-E-N-T-I-A-L, differential equation is what's going to be new in these applications. All right, so far you had the derivatives, and if we had a problem like y equals 3e to the 5t, or y equals 10e to the 5t, or y equals e to the 5t. Let's look at the derivative of each of these. Let's look at the derivative of each of these. All right, what is the derivative of 3e to the 5t? 3e to the 5t times 5. Okay. What's the derivative of 10e to the 5t? 10e to the 5t times 5. And the derivative of e to the 5t is e to the 5t times 5. Okay, so now all I'm going to do is play with this to tell you how I'm defining a differential equation. And let's use an orange here. Is that orange? What I want you to notice is in the derivative, we have actually the function y there. So I could write the derivative in terms of the original function, and I'll just write it as 5 times y. In the second example, the derivative is the original function times 5. So the derivative is 5 times y. And the same thing with the last example, 5y. Okay? This is called, in a simple form, a differential equation. It's an equation. This is called a differential equation. It's an equation, for one thing, because it has an equal sign, right? As soon as you hear equation, don't you think equal? All right. it has a derivative in it. It has a derivative in it. And it's also written in terms of that function y, which the only thing we know is y is in terms of t. Maybe I was given some information about y. But it's an unknown function. So I have the derivative. It's an equation. It's written in terms of the original function. And that's called a real simple differential equation. Okay? Now what we would say is that remember, derivative is a rate of change. If you use words, you would say the rate of change or rate of growth or rate of whatever is proportional to, all right, so is means equals, rate of change is the derivative, is proportional to means it's going to be some kind of constant times it, the function. The rate of change is proportional to the original function. That's what the way we'd read this. If this was a population, you would say the change in the population is proportional to the size of the original population. Okay, if it's a population, and that's the way we'll see it. The change in the population is proportional to the size of the original population, because your original function would tell you size of population. All right, now the question is, how do you go from the differential equation back to the original function? And to go from the differential equation back to the original function is, the original function will be called the solution to the differential equation. So to go from here back up to here, this thing would be called the solution to the differential equation. All right, now at this point in this course, I just have to tell you how it works because you haven't gone far enough in calculus to see how you get there. All right, so this little number right here, by the way, is called a growth constant. I'm having to tell you a lot of things. This really isn't all that bad. The number is called the growth constant right here, and that becomes in the exponent with the e. If that were a negative number, it would be called a decay constant, and it would go up in the exponent with the t. Okay? All right, so the solution to this, to go from here to here, you really wouldn't know if that was a 10 or a 3 or a 1 because all these differential equations we already see 3 possible solutions. So what you would memorize is the solution to this, the solution to this type of equation where it's a constant times y. It has to be this form, a constant times y. The solution is your initial y sub 0 e to the growth constant, k, we usually call it a k, or r, 5t. All right, so the solution to that differential equation is going to be the initial amount e to the growth constant or decay constant t. And you would have to to know what y sub 0 is, you would have to be told what the initial is. For here, the initial would be 10. For here, the third example, the initial would have been 1. For the first one, the initial would have been 3. Okay? All right, so let me say what I said, because it seems like I said a lot, and then I'm just going to tell you how it is. Okay? All right. Whenever we have a differential equation, a derivative equal to a constant times the function, only this one, this is the only differential equation you're learning how to solve. We say that the rate of change is proportional to the size of the original function. When we have a differential equation in that form, the solution is basically shampoo. P sub 0 e to the RT. Okay? All right, so let's put it in the correct symbols and go for it. Since we're doing most everything with population, let's write it like this. dp dt is equal to RT, where P is some function of T. P is a function of T. Okay, but we don't know what the original function is. All right, so the change in the population with respect to time, and that might be money, bacteria, radioactive substances, is proportional to, that R is a constant, either a growth constant or a decay constant. The change in the population with respect to time is proportional to the size of the original population. This is the differential equation. The solution is shampoo. P of t equals P sub 0 e to the RT. Okay? And that's what you want to memorize. Once you get your problems in the textbook to this position, then you're back in your pre-calculus course. All right? And if you took the derivative of P of t, if you take that derivative and write it in terms of P, it would be dP dt equals RP. Okay, so here's your check. If you take the derivative of P with respect to t, it will be P sub 0 e to the RT times R. This part right here is your P of t, so dP dt equals, and sometimes you'll see it P of t written, most of the time you just see P. You could say P of t times R, or RP of t, which is back right here. Okay? There's your check. Everybody got it? So the solution to our differential equations, because we're only going to have one type, is what? Shampoo. P sub 0 e to the RT. All right? Let's go to the textbook. Let's put this into use. All right, I'm on page 284. This is exercises 5.1, and we're going to look at problem number 2. We're going to look at several, but we're going to start at problem number 2. Okay. Can you see it? Okay. Growth of bacteria. Approximately 10,000 bacteria are placed in a culture. All right, translate that for me with symbols. P sub 0 is 10,000. Whatever you're starting out with, that's your initial size. P sub 0 is 10,000. Okay? Let P of t be the number of bacteria present in a culture after 10 hours. T hours. So P represents how many bacteria there are after T hours. And suppose that P of t satisfies the, what's that word? Differential equation. All right, so we have P prime of t, which is the derivative of P with respect to t, the change in the population with respect to time, is proportional to the size of the original population P. Do you see that? All right. Part A. Your book is trying to be gentle. It says find the formula for P of t. Mathematically, it's finding the solution to the differential equation. Okay, so I'm just going to make a little note, and I hope you will. This means find the solution to the differential equation. Not difference equation that we did at the beginning of the course, but differential equation. Okay? All right, so you've memorized the solution to the only type of differential equations we're doing in this class is what? Shampoo. So give me the formula. Okay, and what's your R going to be? I heard a RT. 0.55. All right, so here we go. We have P prime of t equals 0.55 P of t. So part A says find the solution, and you just told me that shampoo e to the 0.55 t, correct? Is this bacteria growing or dying out? Growing, because your R here is positive. All right, part B says, well, what is P of 0? Okay, I've been using the symbol P sub 0, but that means what is the population at time equal to 0? And the problem told you it's 10,000. So therefore, we now have built our solution to be that P of t is 10,000 e to the 0.55 t. All right, so there is the formula that describes how many bacteria we have at any time t where t is in hours.
So in part A, we don't need to put the 10,000.
You know what? That's always seemed, his question was, why didn't we just go ahead and put the 10,000 there? I would have, but I happened to see that question B was wanting to ask you another question. I would have put the 10,000 right there to begin with.
Okay.
I usually don't ask part B. I say find P of t, and I expect P of t to be what it is. All right, they were just trying to be nice, I guess, and lead you through every little thing. All right, everybody good so far? All right, part C says, how many bacteria are there when t equals 5 hours? All right, hope you got your book. I didn't put it under there, but it's part C right here. How many bacteria are there after 5 hours? My question is, am I going to put it into the derivative or into the solution? Yeah, because P of t is number of bacteria. Okay? So how many after 5 hours? So we'll look at P at 5. And we have 10,000 e to the 0.55. And we'll multiply that times 5. Let's do a few calculations here. Here we need to take care of exponents first. 0.55 times 5. 0.55 times 5. And now I need to raise e to that. Okay, so e to the 0.55 times 5 is what? 15.64263. And multiply that times 10,000. And I don't think we can have part of a bacteria, do you? We might have one in the making, but altogether we have 156,426 bacteria. Okay? 156,426 bacteria present after 10 hours. These little suckers are growing quickly after 5 hours. Okay? Everybody good? Students usually beg me for these questions on the test. All right, part D says, what's the growth constant? Yes, that's just terminology. 0.55 is the growth constant. All right, part E and F are my favorite parts to the question. So what does that mean? Probably on the test, because that's the only new stuff on the test other than solving the differential equation. All right, on the test, I never put in those first words, so let's just go ahead and mark them out. Okay, I usually start with determine, okay, because I want you to be able to read the rest of the question and translate it. All right, determine. Now, what's those words? How fast. Doesn't that make you think of a rate of change? Determine how fast the bacterial culture is growing. How fast is it growing? What is the rate of change? When it is exactly 100,000 bacteria. All right, some symbols. How fast is it growing? So you're thinking of derivative, right? How fast? And we know P is exactly 100,000. So which formula am I going to use? Am I going to use the derivative, because you pretend you didn't see that first part? Or are you using the solution for that, the derivative or the solution? Which one? Derivative, because you pretend you didn't see it. All right, so for part E, let's see that you have everything. It's saying how fast. Well, this dp dt represents change in the population. When it reaches exactly 100,000. All right, let's remember P prime means change in population over change in time. So what are my units going to be in my answer? P represents bacteria, right, in a bacteria problem, and T represents hours. So my answer is going to be bacteria per hour. Okay, So 0.55 times 100,000, that looks like that comes out to be, what, 55,000? Did I multiply that right? 1, 2, 3 zeros? Okay. That is right, isn't it? Yes. Okay, let's look at what this just told us. Graphically, visually. It says at the moment when we have 100,000 of these little bacteria floating around, the change bacteria per hour is going to grow 55,000. So tell me what you think P of 100,000 1 would be equal to. Approximately equal to. If you're at 100,000, the derivative at 100,000 is 55,000. It's going to be, oh, no wonder you couldn't answer a question. I messed up. Let's try. All right. It wasn't P at 100,000, was it? I'm sorry. Okay, pretend you didn't see that. They can't edit the tape, right? So hopefully you just had a mental block during that little time. You thought about something else. All right, basically here we are. Sorry, this is time, and this is population. All right, so whatever the population is, we don't know the time, but we're at 100,000 bacteria. The derivative is 55,000. It's going to grow 55,000 bacteria over the next hour. So at the end of the next hour, here's my t plus 1. How many bacteria am I going to expect at the end of the next hour? 155,000. Because your slope, change in population, up 55,000 over 1. Remember how we use the derivative to approximate the next value? Your derivative at 100,000, whenever your population is 100,000, is changing at 55,000 bacteria per hour. So you're at 100,000. You expect it to go up 55 more thousand over the next hour. So at the end of the next hour, you would expect about 155,000 bacteria. All right, everybody good? I can't tell if you are or not. Yeah, we've done this. Rate of change derivative tells you like marginal cost, marginal profit, how many more at the end of the next hour. All right, but let's go back to the question and make sure we know why we use the differential equation. We want to know how fast is it growing. We want to know the change in the amount of bacteria per hour. How fast are the bacteria growing when we have a population of 100,000. So by substituting 100,000 for our population, we see that we're growing at 55,000 bacteria per hour. Okay? All right, let's look at F. And I want you to tell me which equation you're going to use in F. Can you see it? There you go. What is the size of the bacteria culture? So what am I going to be looking for? What symbol? Size of the bacterial culture? P of T, right. When it is, y'all read this next part for me. Okay. When it is growing at the rate of 34,000 bacteria per hour, what symbols is that representing? The derivative, right? That's the derivative. So the derivative is 34,000. We need the size of the bacteria when it's growing at that rate. All right, so we're looking for P of T. We're given a derivative. Which formula am I going to use here? The P of T formula here or the derivative? Obviously the derivative since you were given the information, right? All right, so let's write it out again. We have the derivative equals 0.55 P of T. All right, we're told that it is growing at a rate of 34,000, and notice the units, bacteria per hour, change in P over change in T. And it asks for what is the size of the population culture? What is the size of the bacterial culture? So we have everything we need to solve this question. So P of T then is 34,000 34,000 divided by 0.55. And let's see what we get here. 34,000 divided by 0.55. And this is what I got. Did I hit all the zeros right? Yeah. 61,818. Do I need to use any decimals here?
No.
I don't think so. These are bacteria, aren't they? Bacteria. All right. We don't know exactly when that is happening. We just know when they're growing 34,000 within the hour, this is how many should be in our little dish right then. Okay? So do you see how if you were working in a lab, you could have some bacteria in there, just count what the growth is over the next hour, then you'd have a good idea how many bacteria were there to start with. Okay, so you just sort of keep up with it. Or you have some record that tells how fast they're growing, and you know how many you're starting with, so you know how fast that germ is spreading. You know, there's a lot, when you're in a university setting and you're in classrooms with no windows and somebody's coughing, the germs just grow and grow and grow, right? So you can look at how things are growing exponentially. All right, everybody good on that? All right, let's do a decay problem, and that would be problem number 14. If you can do the growth, you can do the decay. Okay, question number 14. Too bad it's on two sides of the page. All right. Radium-226 used for in cancer treatments, etc., etc. P of T, number of grams of radium-226. That's in a sample after T hours. T years. Suppose that P of T, which is the number of grams, satisfy the differential equation. Okay, what do you notice about this number here?
Negative.
It's negative. And that's the same way with when you take medication. You put so much medication in your body, and that's why you have to repeat it after like every 4 hours or every 6 hours. They know when you take your medication, it's going to disintegrate. And they've done studies, and they know that if you let that medication get below a certain threshold, your bacteria is going to start growing. So that's why the doctor says, take your medicine every 4 hours or every 6 hours, because what happens is here's the threshold, and if you ever let your medication get below it, then the bacteria starts growing faster. So you take your medicine, it disintegrates, and when it's about to get here, you have to take medicine again so that you can keep it in your body so that it doesn't go below that threshold and your bacteria take off growing, or your virus or infection or whatever it is. So that's why they say, even though you start feeling better, you keep taking it because you have these little bacteria hiding down here just waiting for that medicine to get out so it can just grow again. So you have to take it long enough to kill the bacteria. So now you know. All right. So anyway, part A, find the formula for P of T. What did everybody think when you saw that? Find the formula for P of T? Find the solution to the differential equation. I know. Difference was what we studied in the beginning. All right, I want everybody to do A, B, and C real fast so I can flip the page. All right, that probably took you half a second, didn't it? All right, what is I'm going to do A, instead of formula, I'm just going to say, what is the solution to this? Just tell me. 12 e to the negative 0.0043 t. Perfect. Everybody good? All right, what was the initial amount? 12. What's the decay constant?
Negative
0.00043. All right, flip the page. We're just going to say how we would do part D, and then we're going to get in E, F, and G. All right, part D, top of the page. approximately how much of the radium will remain after 943 years? How much will you have after 943 years? Which formula are you going to use?
The function.
The solution, right. Because this says how much there is. T is years. So if you put in 943 for T and did all the calculations, it would tell you how much remains after 943 years. All right, so part E is the one that, I don't know why y'all don't look at the end part to that question. Okay, part E, how fast? As soon as you hear the word fast, everybody's going rate of change. How fast is the sample disintegrating when just 1 gram of this substance remains? How do you know you're using the differential equation? Because it says how fast, rate of change. All right, let's see what parts you know here. 1 gram remains in symbols. What is that into my differential equation? That's your P of T, right? P of T is the amount of grams. So how fast? Now, what would your units be? Grams per year. So in part E, your answer is going to be in grams. What's that, GR? I know, but I mean, what's the symbol? G, isn't it?
G.
G. Grams per, it's been a little while since I did the chemistry, sorry. All right, physics. Grams per year will be your units in part E. All right, and how fast? You would just put in 1 for P of T. And what would your answer be? That's pretty easy if that's just 1. Negative 0.00043. Tenths, hundredths, thousandths, 10 thousandths, 100 thousandths. So it's 43 hundred thousandths grams per year is how it would be disintegrating. Okay? All right, let's look. Everybody good? Let's look at F. What is the weight of the sample when it is disintegrating? Everybody read it. At the rate of 0.004 grams per year. All right, so what is the weight of the sample? Which equation are you using? You're using the derivative. You're told that it's disintegrating. And by the way, when it disintegrates, you need to make that negative. So in part F, it's disintegrating, so you got negative 0.004 equals negative 0.00043, and you're looking for the weight of the sample, which is P of T. Right? The disintegrating tells you, the word disintegrating says you're going to make that negative. Okay? And that will tell you the weight of the sample. Okay? Everybody good? And let's go to part G. It's talking about half-lives. In part G, it tells us for this, the half-life is 1612 years. Okay, so we're starting out with 12 grams. So the first part of the question says, okay, so if I start out with 12 grams, how much will I have left in 1,612 years of this substance? It goes to 6 grams. Okay, it doesn't disintegrate very fast, does it? And the next one is 3,224 years. Well, that's just doubling that, right? You have 0 to 1612, doubling that, you're at 3,224. All right, so here you're at 6 grams. This is another time period here of 1612 years to get to 3,224 years. How much will be left then? 3 grams. That's why when you have a radioactive substance, they have to be really careful about the containers they put it in and where they put it, because if it's bad for you, you don't want it to start leaking if it's going to take 3,224 years to get from 12 grams down to 3 grams. Okay? And sometimes they put I read an article once where they put some radioactive substance in some containers to bury them in the bottom of the ocean. And what? You sort of guess what happened. They didn't take into effect how the salt and the currents were going to corrode the containers as fast as they did. And in no time at all meaning, less than 50 years, they started leaking, and so it was getting into the ocean. So you have to, if there's something you're trying to get rid of, you got to really make sure you look at it from all angles, that the containers will withstand whatever the environment is, because you don't want this stuff getting out. Okay? All right, if it's bad for you. All right, everybody good on that? It's not too bad. Let's go to money. Let's go to money. This is on page 292. We're in section 5.2. 5.2, this is our money problems. And when we have compounded continuously, and hopefully this was derived for you in your pre-calculus class. If not, probably has it in here a little bit. I'm not sure if it does or not. Yeah, it does derive it for you quickly on page 289. But it's P of t equals P sub 0 e to the RT. Same deal, money compounding continuously. All right. 8% compounded continuously is pretty close to 8% compounded daily. People hear compounded continuously and think they'd be rich by afternoon. That's not true. It just grows about at the same thing as daily rates do. And the thing you don't get upset about is, even though we don't have compounded continuously, is that interest rates fluctuate anyway. So when you're trying to make a long-term decision, you just have to make a good educated guess about what you think you're going to average on your money anyway, interest rate wise. So it's a good little tool for doing some estimating. All right, we're going to look at problem number 2 on page 292. Okay. All right, they're just going to use different symbols. They're using A's instead of P's. It's still the same problem. Don't let the letters change you around. They're going to use A for the balance in the savings account after T years, and suppose that A of T satisfies the differential equation. The derivative equals 0.045 A at T, and A sub 0 is 3,000. Okay, so if you want to just replace those with P's, that's perfectly great. How much money was originally deposited into the account? You don't have to worry, you don't get too many of these questions on test. 3,000. What was the interest rate being earned? 4.5 what? How? Compounded continuously. There's a difference between 4.5% compounded annually, monthly, quarterly, daily, continuously. This shampoo answer is only going to work when it's compounded continuously. All right, so be sure when you say interest rate, it's 4.5% compounded continuously. Don't forget that little part. All right, take a half a second and tell me what the solution to this differential equation is. All right, what is it? We'll do it with A's just to show that we can adapt to whether it's a A or a P. A of T equals what? 3,000 e to the 0.045 T. Perfect. Everybody good? All right, part D. Part D is kind of an insult to your intelligence at this point, right? What is the balance after 5 years? What do? Plug a 5 in for T. All right, E, what are you marking out? Okay, the reason they needed you to use part D is because you need what the balance is after 5 years to answer part E. Determine how fast the balance is growing after 5 years. So you needed a balance from part D to put in here. Okay, just tell me, how do you know you're using a differential equation here? How fast is it growing? when you know the balance A of t, you just put it right there. And what will the units be for the derivative? But the money is in terms of what? Dollars per year. All right, so A prime of t is change in dollars over change in years. So your units would be dollars per year when you do your derivative. Very good. Okay, part F, how large will the balance be when it is growing at a rate of $270 per year? The $270 per year represents the derivative, right? The derivative, so so for part F, you'd have 270 equals 0.045 A of t. It's asking what is the balance when it is growing at $270 per year. Okay, so what would you expect on a test? Well, I've been making up these tests for a long time and I'm not very creative. I usually give you a differential equation, and I generally give you something that requires you to use that differential equation because that's the only new part to the course. All right, so that's normally what I do. Look at some old tests and you'll see that's what happens. All right, so using the differential equation, finding a solution. I may ask you to find a solution to a differential equation. I mean, that's new also. All right, solutions and using it. All right, everybody good? All right, we are ready to jump on chapter 6. Very, very, very important. So let's put a few stars around it. Chapter 6.1, very important. It's called anti-differentiation. It's also called integration. Integration. Okay? All right. And we always like to start with where we've been and build on it. So far, we can find the derivative. We know how to find a derivative. For example, I'm going to write down a couple problems. Y equals x squared. Y equals x squared plus 7. Y equals x squared minus 10. Let's take the derivative of these three problems. The derivative of x squared is 2x. The derivative of x squared plus 7 is 2x. The derivative of x squared minus 10 is 2x. Okay, anti-differentiation means if I give you the derivative given, find the function. Okay, well, the function, this is really a little differential equation. It just doesn't have defined in terms of the original function. Find the function. Well, if I give you 2x, we see three examples of solutions to that well, it is a differential equation. When you're looking for the function, we see three solutions here. But what do you notice about all three solutions? How do they differ? By some constant. So we would say the solution is, the function is x squared plus some constant c. Now, in order to know what the c is, I would need an initial condition. When x is 0, what is y? When x is 0, what is y? And that would help me find c. So the value of the function at 0 is going to be your c value there. For an algebraic, I have to be really careful. For an algebraic function. Right this minute, that's the way it looks. All right, so in calculus, what we normally do is we use different symbols to say, I want to find the function for which this is the derivative. And that's the integral sign. That's called the integral sign, I-N-T-E-G-R-A-L sign. And in here we put what the derivative is. So this part is the derivative. And of course we have to have a way of telling what the variable is, and I could go on a 20-minute explanation of this. I'm just going to say this is the way it is. But when we put the dx right here, that says that this is a derivative with respect to x, and it tells me the variable. So if I had like 2t, this would be dt. If I had 2z, this would be dz. That tells me what the variable is. So if I had 2x and this was a dz, then this would be no more than a constant there. That x would not be a variable. Do you see what I'm saying? It tells me what the variable is. All right, this little part, by the way, I don't think it's in your book. It's called the integrand, just in case you want to know that. Integrand, the integrand. The integrand is saying this is the derivative. This says anti-differentiate that. Tell me what the original function is. And so because we already know this answer, we're going to say that's x squared plus c. Now we're going to have some rules so we don't have to sit around and guess this in just a minute. Some rules. All right? Now, once I find the answer, how could I check it to make sure that I'm correct? How could I be sure that this represents all functions for which this is the derivative? How would you check? Yeah, just take the derivative of this. This is your function. Take the derivative and you get 2x, and you're back to here. So when you get your answer, you can always turn around and check it. All right. By the way, this is called an indefinite integral. An indefinite integral. Later we're going to look at what's called a definite integral. But right now this is just called an indefinite integral. All right. So suppose I give you the integral of e to the x dx. What's the question you're asking yourself? What is this part right here? Derivative. So I'm saying, what is the function for which the derivative is e to the x? Oops, e to the x. This part right here is the derivative. And everybody says, okay, what do I take the derivative of? Gets me e to the x. And everybody says, e to the x. All right, so this is the function for which this is the derivative. And we put the plus c because there are a zillion functions for which that's the derivative, but they just differ by that constant. All righty. What are you asking yourself when you see this?
Where 1 over x is the derivative.
Good. Say it to your neighbor. Everybody.
1 over x is the derivative. 1 over x is the derivative of the function.
Okay. So what is it that you take the derivative of that gives you 1 over x? Okay, it's natural log of x. But now I need to do one more little thing to you. It's absolute value of x plus c. And I'm going to quickly tell you why. They have that in a little orange definition or somewhere in a previous chapter. What happens is y equals just plain old natural log of x when x is greater than 0, right? Because you can't take the log of a negative number. If x is a negative number, then you would be looking at the log of a minus x. For example, if x is like negative 3, if we did an absolute value, it would be the log of minus 3, right? If you had an absolute value here. It's really my definition of absolute value. So if I take the derivative of natural log x, it's 1 over x. If I take the derivative of natural log minus x, that's the derivative of log u. What's that derivative? Log u. 1 over the u times the derivative of the u part, which is negative 1, which comes out to be 1 over x. So if x is greater than 0, the derivative of natural log x is 1 over x. If x is less than 0, the derivative is still 1 over x. So when we have the integral 1 over x dx, you must remember, unless you want to lose some points, that it's the natural log of the absolute value of x. Okay? All right, let's try another example. Suppose I want to integrate 4 e to the x dx. What do you bet that answer is? This is the derivative. What do I have to take the derivative of to give me 4 e to the x? And I think I hear everybody saying 4 e to the x plus c. All right, this is a constant times e to the x. Remember when you had a derivative and you had a constant times a function? The derivative is the constant times the derivative of the function. So this is just the reverse process. If you have a constant times a function and you're integrating, the answer is going to be the constant times the integral of e to the x, the antiderivative. All right, so let's try another one. Suppose I have the integral of 5 over x dx. That's the same thing as 5 times 1 over x dx, right? So what's that equal to, everybody? 5 times natural log what?
Absolute value.
Thank you. Absolute value x plus c. All right. Try to get your attention there. Absolute value of x. All righty. Suppose I have, all right, this is a good one. 5 dx. Right. What do you take the derivative of that's just going to give you plain 5? Yes, 5x plus c. Very good, very good. 5x plus c. All right, well, let's go to some rules so you don't have to use your brain too much. I'm on page 321, rules. Page 321. And at this very moment, we're only going to work on 2 rules on this page because the other one we're going to get right out of section 9.1, which I'm going to go to anyway now in a few minutes. All right, page 321, the first rule. The integral of the variable x raised to the r. That's not a function of x, is it? It is the variable x raised to the r. So that you don't have to sit there and guess a half a day what the derivative is. Remember when you took a derivative, you brought the r down, rewrote decrease by 1. Integrate, you increase by 1. I don't know if y'all heard this. Differentiate, decrease. Integrate, increase. Don't you love that? So when we have x to the r, when you differentiate, you brought your r down, rewrote decrease by 1. When you integrate, you're going to increase your r by 1, but you also have to divide by that so it sort of cancels itself out. And you can see the check on this. This is the function for which this is the derivative. So if you were going to check it, you would bring r plus 1 down in front. They're going to cancel out. X to the, when you subtract 1, you would be back to your r. So do you see your check there? So x to the r, when you integrate, you're going to increase that exponent by 1 and divide by that same number. Of course, r cannot be negative 1. If r is negative 1, what would this x to the r look like? If r is negative 1, what does x to the negative 1 look like? 1 over x. And when you integrate 1 over x, what do you get? Right there, down at the bottom, natural log. So that's when r, this is the case where r equals negative 1 when you were looking at x to the r, correct? Okay, so that's why you have that little restriction in there. All right, everybody got the rule? All right, so let's see what I can do to you. All right, so we're going to do a little drill. We're just drilling this moment on x to the r dx. Okay. Square root of x dx. Okay. Integrate square root of x dx. All right, so it's x raised to the r. You're integrating. So you're going to add 1 to that exponent, divide by that same exponent, and put a plus c there. All right, so x to the 1/2 plus 1 will be x to the 3/2. Divide by 3/2. And you know when you divide by a fraction, you just invert and multiply. So it'll be 2/3 x to the 3/2 plus c. All right, let's do a quick check. A quick check. Your answer is the function, and when I take the derivative of this, I better be back to square root of x. All right, so let's do the derivative. So I have 2/3. I'm doing a derivative, so I'm going to bring down the 3/2, rewrite, decrease by 1. And then the derivative of a constant is 0. So 2/3 times 3/2 cancels out. 3/2 minus 1 is 1/2. And we're happy. Check. Everybody got it? Questions? Everybody good? Okay, let's try another example. We want to integrate 1 over x cubed dx. 1 over x cubed dx. All right, does this match the form exactly x raised to the r? This is 1 over x cubed. So before you can apply the rule, it's got to match it exactly. How do you need to rewrite that? Good. X to the -3 dx. All right, so now we're ready to go. We're going to add 1 to the -3, so that's x to the -3 plus 1. We're going to divide by -3 plus 1 and not forget the plus c. That will give me a x to the -2 divided by -2 plus c. And if we rewrite this without the negative exponent, what are we going to have? A -1/2 with the x squared in the denominator plus c. Carry the x to the -2 down in the denominator. Is that good, everybody? All right. Just a second ago, you integrated 5 dx for me or something like that. How would I make this rule work? What would r have to be if I were going to try to apply that rule? How would you rewrite 5? If I need to get an x in there, I'm trying to make you mind readers. None of my x to the 0. All right, we could rewrite this as 5 times x to the 0 dx. If I need to get an x in it, x to the 0 is equal to 1. All right, so if we wanted to integrate that, it would be 5 times x to the 0 plus 1 over 0 plus 1 plus c. And that would give you 5x plus c. So if you didn't want to memorize that if you integrate a constant, it's just going to be a constant x, you could go back in and put it times the x to the 0 in there. Everybody good? All right, ready for the next example? I just lost my train of thought. What was it going to be? Okay. Suppose you wanted to integrate the quantity x plus 1 squared dx. This is the only rule we have. Let's brainstorm a second. That's a good start. I'd do that too. Let me think here. What are we going to do? If this is the only rule we have, what do you think we would need to do here? Multiply it out. Okay, so we're going to expand the product, and that would be x squared plus 2x plus 1 dx. And keep remembering, this is the reverse process of derivatives. So remember when you had several terms and you were doing derivatives, didn't you take the derivative term by term? So now we're going to integrate term by term. So we integrate term by term. Integrate term by term. All right. If you integrate x squared, everybody, what are you going to get? Follow your rule. X to the third over 3 plus, and this is just a constant times x, so it's 2 times. If you integrate x to the first, what are you going to get? X squared over 2, right? Which I know the 2's will cancel out there. Plus, if you integrate 1x plus c. So it simplifies to x cubed over 3 plus x squared plus x plus c. Okay, all right. This was not the variable x raised to a power, but a function of x raised to a power. So at this point, the only thing we know how to do is multiply it out. Integrate term by term. If you integrate x squared, if it's this part, that would be x cubed over 3. 2 times integrate x, x to the first, x squared over 2. You can think of that 1 as 1 times x to the 0. 0 plus 1, x to the first over 1, plus c. All right, how do we check that to make sure we're right? All right, let's find the derivative. If you take the derivative of x cubed over 3, you're going to get, bring the 3 down, they cancel out, you got an x squared, right? If you take the derivative of x squared, you got 2x, derivative x is 1, you're back to here. If this is my original problem, that factors to x plus 1 squared. Check. Okay. Everybody good? All right, let's try another. I don't know how hard to go for you. Not too hard? All right, let's just go to the textbook exercises then. Normally you would want hard, but today you don't. All right, I'm on page 324. Page 324. And we're at exercises 6-1. And we're going to hold off today on these e to the 3x's because they're just going to try to tell you a formula to memorize, but we're going to learn how you do it in 9.1, which is the very next thing we're going to do anyway. All right, it says find all antiderivatives for each of the following. So this is, I want to find the antiderivative of this. What is the function for which this is the derivative? Don't let these symbols mess you up. It's saying anti-differentiate. So really, this is the derivative, find its function. So what would that be? If you integrated x, you get x squared over 2 plus c. Plus c. Yeah. Right. It does seem a little strange. Actually, what they used in the book in the definition was a big F. Let's see if I can find that for you and show you how they did it. This is the page 320. This integrand part right here, they're expressing as f of x, but that really is the derivative. And then they use the answer as being the big F as the function. And I told you, just think of this as the derivative and this as the function. Okay? And that's all it is, just different symbols. All right, so back here, problem number 2. If you're told to find the antiderivative, what would you say this one is? 9x to the 9th over 9, so that simplifies to x to the 9th. What would you say number 5 is? 3x plus c. I was forgetting my plus c's. All right, so this question right here, find all antiderivatives, is the same thing as using the integral sign, like the integral of 9x to the 8th dx. Okay? All right, what's the answer to number 7? Integrate 4x cubed dx. What's the answer?
X raised to 4 plus.
Okay, 4x to the 4th divided by 4, right?
Plus c.
Plus c. Add 1 to that 3. All right. I want you to take a second and do number 14. What is it? Should be easy. How are you going to rewrite that to make it look easy? All right, it's the integral of 1/7 times 1 over x dx, right? And that's just a constant. So it's 1/7 what? What do you integrate? What do you take the derivative of that gives you 1 over x? Natural log what?
Absolute value.
Yes. All right, so that wasn't so bad. How would you handle number 15? The integral of x times the square root of x dx. Is it in the form x to the r? What are you going to need to do in number 15? Yes, you are so good, good, good. In number 15, you had the integral of x times x to the 1/2 dx. That's a product. We know how to integrate term by term when it was added, but we got to find a way to simplify this before we can use the x to the r. So when the bases are the same, you add those exponents, right? So we have the integral of x to the 3/2, x to the 3/2, and now we're ready to integrate. So when we integrate, we're going to add 1 to it. So 3/2 plus 1, I think, is 5/2, right? Add 1 to that, plus 2 2's. Divide by 5/2 is multiplied by 2/5 plus c. Okay? Do I see any confused looks? It was a product. I had to find a way to simplify it first. Now it's a good old x to the r. So we just add 1 to 3/2. 1 is 2 2's, that's 5/2. Divide by 5/2 is multiplied by 2/5. Okay? All righty. we have about 15 minutes left, and I want to start giving you a flavor for integration by substitution, because we actually need to do it a couple days so it really sinks in. All right, and know for sure that I'm going to come back to this. All right, this is 9.1, very important. It's called integration by substitution. And what I want you to recall is back in the days of derivatives. Recall, when we worked with derivatives, we had problems like y equals x squared. Then we went to problems like y equals 3x to the fourth plus 1 squared. Okay? Originally, we had the variable x raised to a power, and then we took the derivative. Later, we went to a function raised to a power. What rule did we use here? Chain rule, or really the general power rule. So when you had a derivative here, of course, you had 2x. But when you had a derivative here, you brought the 2 down, rewrote exactly, decreased by 1, derivative of the inside. Okay, integration by substitution is going to follow our general power rule when we had the algebraic functions, the chain rule for exponential and log. Okay, so integration by substitution is going to be a reverse process of our general power rule or chain rule. Okay. All right, so integration by substitution is a reverse process of general power rule or chain rule. Okay. All right. Next semester in your next course, remember you've learned the product rule for derivatives. That reverse process is going to be called integration by parts, and that is not covered in this course. All right, but when you have a product integrating, it's going to be a reverse of the product rule. All right, here we go. Going to take a simple problem, and we're going to make a comparison here. All right, we want to integrate something like x cubed dx versus 2x plus 1 cubed dx. All right. When you integrated x cubed dx, we know that's x to the fourth over 4 plus c. But the concern here is it is not the variable x raised to a power. And if it was squared, we would just multiply it out, do it term by term. But a cube or a 10th power, it starts to be a little more complicated. So what we're going to do is use a method that's called U substitution. And it basically goes like this. We're going to convert this to a really, really simple problem with only u's and numbers in it. And then it will follow my little rule, x to the r, which are u to the r. We're going to try to send it to a u to the r du, where the u is my variable. And if I can get it to u's, it'll just be u to the r plus 1 over r plus 1 plus c. Okay? All right, u substitution. All right, here's the way it goes. You have to decide what you want your u to be so it'll look like a simple u to the r. Well, what would you need u to be here so it looks like a u to the r? You're very good. So we're going to we're just picking this, u to be 2x plus 1. All right, now this is what I like to do. As I am doing this problem, I usually put this out to the side. This is looking a little messy here. I'm going to come right underneath, and as I do every little part, I'm going to put it there. I'm trying to make it look like a u to the r du. So now we have u, the 2x plus 1 was my u, and the r is the 3. Okay, now what else do I need in my formula to make it look like this? Du. Now, where in the world do I find a du from here? Take the derivative, absolutely. If I take the derivative of u here, it's going to be with respect to x. So du dx is 2. All right, but I'm going to need to find where that du is. So remember, du dx is change in u over change in x. So I'm going to multiply both sides by dx. So I get du equals 2dx. All right, just multiplied both sides by dx. Okay? Now, here's where we're going. There's the u, the cube. I've got to make an exact replacement for dx. Do you see what dx is exactly equal to right here? 1/2 du is dx. I got to substitute right here. So now I have 1/2 du in the place of the dx. All right, now let me just rewrite the problem a little bit. That's 1/2 u cubed du. Is that going to be easy to integrate?
Yes.
Yes, it is. That's a constant, u to the r du. So when we integrate this, we're going to get 1/2 what? U to the 4th over 4 plus c. All right, now what have we done? We've taken a complicated problem, converted it to u's, integrate it really easy. Am I done there? No, because the original problem had x's in it. So we got to go back and put in what it is. All right, so we have equals u, which is 2x plus 1 to the 4th over 8 plus c. And that is going to be my answer. And we're going to check it just to confirm that. If you integrate 2x plus 1 cubed dx, it's going to be 2x plus 1 to the 4th over 8 plus c. This is the function, all functions for which this is the derivative. Let's come over to the side and just do a quick check. If y is equal to 1/8 times 2x plus 1 to the 4th plus c, the derivative is bring the 4 down in front, rewrite, decrease by 1, derivative of the inside. And then the derivative of a c is 0. Okay, 4 times 2 is 8. The 8 over 8's cancel out. And there is my integrand right there. Not bad, is it? All right, explain it to your neighbor because you need to mumble through what all that was. Everybody talking.
Yeah. You mean multiply. Oh. Oh, okay.
Okay, this is not totally trivial. Would anybody be brave enough to come up here and explain this problem? Extra credit. You need to give me extra credit for letting you come up. Anybody willing to come up and explain this problem? Because if you can explain it, you got it. Anybody? I'll give you another chance tomorrow. Let me tell you what it is. All right. How did you know you were going to need to go to substitution here? A function raised to a power, not the variable x. And the reason we're going to go to u substitution is we're going to change it to a really easy problem. All right, so you're trying to make it look like a u to the r, so you all picked that u was 2x plus 1. So I wrote down the integral sign. I put a u Here's my 3. And then the next thing I notice is I got a dx there. I got a du over here. The only way I can get a du and a dx is take the derivative of u here. So we took the derivative. We know that du dx represents a change in u over change in x, so we can multiply both sides by dx. Now we're making substitutions into the original problem, so I got to come up with a dx. So solving this for dx, I see that is 1/2 du. 1/2 du. All right. Now I just rewrote it so it looked prettier. It's the integral 1/2 u cubed du. So the 1/2 is just a constant. You now have your perfect u to the r. And bingo. You got it. All right, we got 2 minutes. I want to see who can get this right quickly. I won't make it hard. I will not make it too hard. All right. The quantity 3x squared plus 1 raised to the 4th times x dx. You're going to make it look like the integral u to the r du is your goal. You always find your u, make the substitution, and then go directly to the derivative and hope everything falls in place. Did you get it? What'd you get?
One over 30 times
1 over what?
30.
30?
Yes. Over the power u to the power 5. U is 3x squared plus 1.
And this is raised to the
5.
5. Anybody else get that answer?
I'm pretty sure it's right.
I think he's pretty sure too. I think that's right. All right, did everybody pick u to be 3x squared plus 1? All right, you always go through the same steps every time. Come right underneath u to the 4th. All right? Don't worry about anything else in there until you come and take the derivative. All right, so always find your u, then take your derivative. So du dx is equal to 6x. du is 6x dx. Always the same pattern. All right, this is the place where you look both ways. Look both ways. I've got to replace the x dx. Do I see a x dx here? Right there. So x dx is exactly 1/6 du. So we'll come right under the, it's always the same pattern. Find the u, then go find the derivative, find du, look both ways. So exactly x dx is 1/6 du. The whole x dx matches up to 1/6 du. So it's 1/6 u to the 4th du. When you integrate, you get 1/6 u to the 5th over 5 plus c. Did you already know how to do this, or were you just smart? Smart. Good. No, it means that you used great critical thinking skills, that you reasoned through something. Excellent, excellent. All right, 6 times 5 is 30. There's the 30, and there's the u to the 5th. Excellent. Let's call it a day. We'll start here tomorrow. Have a great day, everybody.